Started from where we left off last time. So we sort of got started on chapter 6. We didn't go far really. The chapter will be covering the DC to DC converter topic. So we covered the AC to DC converters, and we covered the AC to AC converters so far, and some forms of AC to DC converters, and some forms of AC to AC converters. This is definitely not the full spectrum of the technology. And then we're going to be looking at DC to DC converters, and then chapter 8 will be the DC to AC inverters. Yeah. So that's so we have two more main topics left. Yeah. Again, under the DC to converters topic, there are many types of converters we will not cover. But they are derivations of the basic topologies that we will cover in the course. And we went through the difference between, we went through the concept of a linear regulator at the very beginning of the course and in the last class, so I will not dwell on that anymore. I think it's the power loss issue is the main difference between the linear regulator and the switching power converter, as we've discussed many times. And we saw that the efficiency of the linear regulator was equal to what? V output over V input, right? So anytime you have V output half the V input, that means your efficiency is 50% already, right? While in a switching power converter, that is not the case. In a switching power converter, we operate these switches like an ideal switch. So it's either on with a very low resistance or off with an infinite resistance. So if it's a very low resistance, then the losses are quite low compared to the case of the linear regulator. But because we end up with a waveform that is sort of a pulsed shape waveform, which is not acceptable to our loads in most of the cases, right? If our load just requires some average power, is this waveform okay or not? If a load just requires an average value of voltage, it will filter out the voltage by itself, right? Then it's okay, right? Motors, for example, motors are driven by inverters. They are power electronic devices, and 99%, 95% of the time, there is no output filter at the output of an inverter. And we will see that inverter output it's like a pulsed waveform like this, right? Why is that the case? Because motors have windings. The windings are nothing but RL series circuits. So these RL series circuits act like filters. So even though you're putting a pulsed waveform of voltage across the motor's windings, the current waveform is a nice, decent sine wave. Not pure, but it's a nice, decent sine wave. And we will see why that is the case when we talk about inverters in the next chapter. So but in certain cases, for example, where motors are connected to inverters or to power electronic devices through a long feeder, the motor is very distant from the power converter. Then, in these cases, we require filters. Why do we require filters? Because have you studied transmission lines effects with 322 or no transmission line effects? Communication transmission line. You have not studied those. Okay, so it's a topic that is quite interesting. But basically, what it says is there are reflected waves, depending on the shape of the waveform and the length of the cable. There will be some reflections of the waveform that you are sending. So if I am sending a pulse that is 1 kilovolt, by the time it goes and comes back, if I'm sending another one, at some point this pulse is going to be twice the value, right? So it's basically the long cables will distort the waveform. I mean, it's a big discussion about the transmission line, but the transmission line phenomena or effect. But the idea is they distort the waveform shape. So for waveforms that have quite a bit of harmonic content, so like pulsed waveforms have, they contain almost an infinite amount of harmonic content, right? If you have a pulse, you have many frequency harmonics or contained in that pulse here. So in these cases, it's if the motor is very far away, then you would require a filter. If the motor is very close to the inverter, there is still no need for a filter because the motor itself, the windings act like the filtering elements. Yeah. So we also talked about the time that the switch is closed, and we called that the duty ratio of the device. So the T on over T on plus T off, and sometimes this is referred to as the on-time duty ratio, as well as you can also find the off-time duty ratio. So the on-time duty ratio would be T on over the period, and the off-time duty ratio would be T off over the period, right? So that's and then of course 1 over the period is also equal to frequency. So that this F is called switching frequency in this case. And we said that that T on and T off is equal to the period, and the duty ratio is expressed as a percentage or a ratio. So the duty ratio of the switch being on plus the duty ratio of the switch being off is always 100%, right? So talked about that. And then we looked at this website, and we will look at it a bit more today. And then we started with our first converter. When we started our first converter, we said we derived the reasoning behind every component in the converter. So we said that this is a step-down converter, and I won't redraw it. So we said that we started off with the basic ideal switch connected to the load that we talked about, that we initially discussed as justification for moving to the switching power converter. And we said that, fine, now I know that across these 2 points here, or what I called V-pole, the waveform for V-pole will look like, this is V input, and this will be the waveform for V-pole. If the switch is on, then V-pole is equal to V input. V-pole is equal to V input. And the switch is off, V-pole is equal to 0 because it's open. Right? So if it's open, there's no current flowing, then there's no voltage at the output. Right? So we said this was the case. This was the waveform here. And we said that the load does not, if our load does not really like something like that, and it would like a nice pure, or nice purer DC, so DC with less ripple. So this is DC plus AC, so it's DC with ripple on it, a lot of ripple. So I would like to reduce my voltage ripple, right? So how do you reduce voltage ripple? We add capacitors. That's anytime you want to reduce voltage ripple, you will definitely add capacitance. So this can do the job, but it will result in waveforms that look like, so I will charge my capacitor here to my input voltage, and then maintain the same. And then during the time when the switch is off, the capacitor will be feeding my resistive load. Correct? Do we agree? This is what would have happened if I just have a capacitor. Of course, I've sized the capacitor properly so that this does not decay all the way down to 0 by the time the next pulse comes through. Right? I mean, if the capacitance is too small, this can go this way. This can do this way and then be 0 and then go back up again. Correct? So I've sized it properly so that this is not the case. Right? If this is what's happening, what am I seeing at these transition points? I'd like to draw the capacitor current in this case. If the capacitor is initially discharged, okay, what's happening here? I'm charging the capacitor, right? I'm charging the capacitor, and I am gonna have to abide by my capacitor current equation. IC equals C dVc by dt. So what did I do here? I'm trying to put a huge voltage on the capacitor, meaning try to change the capacitor voltage instantaneously. If you try to change the capacitor voltage instantaneously, what's going to happen to the capacitor current? It will shoot up very high, right? So you end up with huge spikes in current because of these zones where you're trying to change capacitor voltage almost instantaneously, right? Capacitors don't like that. Capacitors like voltage to rise, right? Slowly. So because of this phenomena, we said, okay, why don't we add an inductor here like we did before to the AC to DC rectifiers? And if that's the case, then this combination here will have less capacitance. right? It will look less like a capacitor, more, it will have some inductance component as well, inductive component as well, yeah. So basically what the inductance does in that case is not allow these huge spikes in current. So instead of now very large spikes in current to charge my capacitor, in a very short period of time, actually this is not correct. Because here this is flat, right? So there's no dV, there's no current actually. The current's only happening where? Where does the current occur? Only at the transit, whenever dV is changing, right? So whenever the voltage is changing. So the voltage is changing only during this part. So that I have huge current spikes only during these times here, and then it's zero, right? So these current spikes are we're gonna go through the switch, right? And I don't want that to happen. I don't want to select a very high current, peak current switch when my average load is very small. So I added this inductor to smooth or for convenience, or to be able to properly operate and design this circuit, right? Otherwise, you would probably not be able to operate this circuit, because not only the capacitors would not like to be, capacitors don't mind if you charge them this fast, but then you have to do what? You have to rate them for very high currents. You have to do that. And then what else? You would also have to make sure that your switch, besides your switch being able to provide these allow these high currents to pass through, your source also has to be able to provide this current. Batteries, for example, do not like to operate in that fashion. Batteries do not like you to draw a huge spike in current for a very short period of time and then stop. They do not like that. That's why the camera flash circuits that we, I think at the very first class or second class, we talked about some equivalent circuits for simple, many different applications. And, camera flash was one example where, we were charging a capacitor first and then discharging the capacitor through the flash circuit. Yeah. Or lasers are the same thing. Lasers are, they require sort of pulsed waveforms to be able to activate your laser tubes or whatever. So you will definitely have some filtering stage in there to allow you to do something like that. Yes, ma'am. No, this was without the inductor. Yeah, this is without the inductor, right? So when I put the inductor, we can draw the current waveform later. But basically, when I put the inductor, I will not have these spikes in current from feeding from the capacitor, from the source, basically, which are due to the capacitor's presence. Right? So the capacitor current actually also has to be feeding, but it's you charge the capacitor during a period of time, then the capacitor current is zero, right, until here, and then the capacitor is now discharging to the resistor, right? This is what the capacitor current would look like. Charging the capacitor, then it's zero, then you are feeding the load again. Then you're feeding the load again. Right? That's what the capacitor current would look like in this case. But now I've eliminated these high spikes and have done my job and added this inductor here. But after adding this inductor, what happened? We know that inductors force or maintain current continuity, right? So if I'm gonna add this inductor to maintain current continuity, and then I have a switch before it that I'm opening instantaneously, we know that inductor voltage equals L di by dt, right? So if I try to instantaneously disrupt inductor current, which is equal to switch current, right? Inductor current is equal to switch current. If I instantaneously try to disrupt inductor current, I will develop a very large voltage across the inductor, right? From Kirchhoff voltage law, forget about, just look at the voltage across the switch and the voltage across the inductor. Okay? Forget about everything else, it's small. Ignore everything else, it's small. If everything else is small, then the voltage across the switch is equal to the voltage across the inductor, right? From Kirchhoff voltage law, around the loop, these two voltages are equal to each other. One with a positive sign, it doesn't matter, depending on the polarity, I don't really care. But from a magnitude perspective, the voltage across the switch is equal to the voltage across the inductor, approximately, if other stuff is small. So if the inductor voltage is very large, then the switch voltage is very large, and will cause these arcs across the switches. And we cannot have these arcs across the switches, otherwise they will burn the devices. So what do we do about that? We have to provide an alternative path for the current to flow. So the alternative path to current for current to flow would be a diode here, for example. If I put a diode here, then if I open this switch, current can flow from the inductor through the capacitor, through the resistive load, and then back through the diode, right? Okay. So now with all of this stuff now on hand, now let's look at the waveforms. Let me redraw this. So this would be, let's draw VP first. VP would be, I'll call this V pole, okay? V pole. VP will look like, if this switch is receiving a gate signal, like this, and is being controlled properly, then VP will look like this waveform here. It will equal V input when the device is on, and 0 when the device is off. And this will be, what is this time here called? Exactly, this will be your switching period T, and it's the inverse of the switching frequency F. You can Fs or Ts, you can call that if you want. Okay, and this time where the switch is on is called the time when the switch is on. It's called the on-time duty ratio or the duty ratio, right? So it's D on, duty ratio of the device being on, and it's equal to the time the device is on over the full period. And it's the same thing with T off or D off. Okay, so this is VP. If this is VP now, what is the function of this combination? It's filtering. This VP is a waveform that has AC component plus DC component. Do we agree? I would like to deliver as much of the DC component as possible to my output voltage. That's my goal, yeah, right? So now, what do the waveforms across all of these components look like? Yeah? So I have to design my capacitors and inductors to make sure that the capacitor, for example, has enough voltage or has enough charge to maintain the voltage across the load when it's not being recharged, right? That's how you design the capacitor. And how would you design the inductor? I want to make sure that the inductor current is continuous for at least one switching period. The same as the capacitor, right? The capacitor is you have to design it so that you're able to store energy for at least, this, part of the switching period. So you can cover the rest of the switching period where the capacitor is not being charged. Same thing with the inductor. You want to make sure that you're able to supply current to this output combination for at least a portion of the cycle where it's not connected to the input, right? Because this is, the inductor, when the switch is off, the inductor current is not being replenished from the supply, right? When the switch is off, you're just the inductor energy is what's supplying this circuit. Inductor energy and the capacitor energy are what's supplying. The reactive elements are what's supplying this circuit, right? Because when the switch is off, current will flow from the inductor through the load, through the capacitor, through the load, and the capacitor current will actually flip at that time, and capacitor current and inductor current will both be supplying the load. So when the device is off, inductor current is supplying the load, capacitor current is supplying the load, and they're both flowing back through here. Okay? So now let's see the rest of the waveforms. Okay, so now this is input voltage. How do I draw the inductor current? I have the equation up here for inductor voltage, right? So VL is equal to L di by dt. So inductor current IL of t is equal to 1 over L integral of VL dt. So it's the integration of voltage across the inductor, basically. So what is the voltage across the inductor? Ideally, if the inductor is very large and there is an AC component, right? Or actually, if there is a DC component, if you're feeding this inductor, this circuit here, with a DC component, what will the inductor look like? A short circuit, right? How about if you have any AC component? If you have any AC component, then this inductor looks like an open circuit, right? Inductor looks like an open circuit, and the capacitor looks like a short circuit to the AC component, right? So all the AC component will be what is now, okay, what's the voltage across the inductor now? The AC component, right? So all the AC component will be across the inductor, right? AC component of what? Of the input to this circuit. So the input to this circuit is right here. It's this V pole. That's the input to this circuit. It contains an AC source and a DC source. If I draw the equivalent circuit in both cases, I will see that for the AC source, all the voltage of the AC source, theoretically speaking, if it's infinitely large, right? We said it's a very large inductor, right? And we said that this capacitor is ideal, and it's a very large capacitor as well. That's why 1 over omega c will automatically be 0, right? So in that case, the inductor voltage will look like the AC component of this waveform. What is the AC component of this waveform? This is a square wave. How do I extract the DC component and only keep the AC component of this waveform? Think of your brain is filtering this waveform. How would you filter this waveform? Remove all the DC out of it and keep only the AC. Exactly. This is a waveform. A waveform that has AC component plus a DC component. DC component is the average value of this waveform. Remove the average value. If you remove the average value of this waveform will just fall down by the average value. It will move down by its average value, right? So you'll end up with a waveform that looks like this. This will be VL. This is a waveform, same waveform, exact same peak-to-peak value, but the average value was removed, right? So if this is 6, 0 to 6, this is minus 3 and 3. Okay, so if this is 6 peak-to-peak, this is minus 3 and 3, right? You've removed the average value. What is the average value of this signal? 0, right? So now this is VL. If this is VL, I would like to figure out what IL is equal to. IL is the integration of the voltage, right? This is the voltage across the inductor. In steady state, what's the integration of this waveform? This is a flat 3 volts. What's the integration of a flat fixed value? A ramp. So if it's integration of 3, it's 3t, right? So it's a ramp. Of course, there's an initial condition, right? But I'm ignoring the initial condition of not being charged. I'm always now charged. So what will be the initial condition every time if I'm in steady state? Let's draw it, and then you'll tell me when I draw it. Yeah. Okay. So this is it's a ramp, right? The flat section is a ramp, a positive slope ramp, a ramp with a positive slope. And I'm asking you what is this I0 here. We'll look at it. We'll look at it after. Let's draw the waveform first. How about now? When I'm applying a negative voltage across the inductor, it's what does the integration of current look? What does integration of voltage look like? Integration of a negative number. It's a negative ramp, a ramp with a negative slope, and it's exactly the same slope because the value here is the same, right? So if it's minus 3, it's minus 3t. If it's 3, it's 3t, right? So the slope of the ramp in both cases is the same. So the slope of the ramp is the same. Before I ask what I0 is, let me ask what you agree that this red line is the average value of this current or not? The red line here is IL average. Do we agree? Okay, what does this average value look like? What is this average value? What is it? Where is it going to go? Think of the same logic. We have a node here now with current coming in it, current coming through to that node, right? This current is now going to be pushed into the capacitor to charge it, right? And into the load to feed it, right? This current is this blue waveform, right? This blue waveform, what is it again? Is it DC, pure DC, or is it AC plus DC? It's AC plus DC, right? So this blue waveform is an AC plus DC component. This blue waveform is coming into this node. This node, there's a capacitor here that we said is very large. For now, it's a very large capacitor. So it's a very large capacitor, and it's seeing a current that is AC plus DC, and so here I have a current AC plus DC, AC plus DC. Where is the AC current going to flow, or where is the DC current going to flow? The capacitor has an impedance of 1 over omega c. Any AC component will see the capacitor, and we said the capacitor is very large, right? So if the capacitor is very large, and I have any AC component, then this capacitor will look like a short circuit. 1 over omega c is 0. 1 over something very large is 0. So it will see a short circuit here, right? So the AC component will flow right through the capacitor. Right? None of it will pass through, theoretically speaking. None of it will pass, theoretically speaking, because I said the capacitor is very, very large. If the capacitor is small, then there's a finite amount of AC component that's flowing into the capacitor, and the rest has to flow through the resistor, right? So, but if the capacitor is very, very large, then all the AC component will flow through the capacitor, and then the DC component will flow through my resistor, go to my load. That's ideal case. So what is this average value of inductor current? It's equal to the average value of load current. I load average, right? So average value of inductor current is equal to the average value of load current, right? So that's going to go through straight to my resistive load. How about the AC component? We said it's going to go to my capacitor, right? So now, what does the capacitor current look like? This is IL waveform. IL, inductor current, IL waveform. How about capacitor current waveform? What does IC look like? We said IC will contain all the AC component of this current. So what is the AC component of this blue current? Exactly. I take this blue current, shift it down by the average value. Right? So if you take the blue current, shift it down by this red value, it will look like something like this. Right? So this is IC. So if this is IC, what does VC look like? Capacitor voltage look like? What does capacitor voltage look like? Capacitor voltage is the integral of capacitor current. Right? So what's the integration of a ramp? Right? It's the integral of this, right? VC is the integral of this. No, IC, I already drew it. Right? IC is going to be the AC component of this current coming through. Right? But now I would like to draw a VC. Yeah, it will be a quadratic. equation. It's a squared relationship. I cannot draw that honestly nicely, but is it like this or is it like this? I don't know. I think it's like this, and then like this, then like this, then it's an x squared and then a minus x squared, right? So it's an x squared and then a minus x squared when it's negative, when the slope is negative here. Okay? So this is what? This is VC. Now this is my voltage ripple. VC is equal to V output, right? VC in this case is equal to V output. So I've seen how all the waveforms look like from on all the components. And now to design the capacitor to allow you to maintain a certain amount of voltage ripple, how would you go about that? This is my delta V. First, does everybody see all the waveforms or not? Is everybody okay with the waveforms? Okay, so now before the capacitor, how would I design? Again, capacitors are there to maintain voltage ripple. Inductors are there to maintain inductor current ripple. So here, this is my delta I for my inductor. Right, this is IL, right? We said this is inductor current waveform. So this is the ripple in inductor current. This is delta I in the inductor current. So if I increase inductance, what's going to happen to this waveform? Yeah, because remember, inductor current is equal to the integration of 1 over inductance multiplied by the integral of the voltage. The voltage was a square wave, flat value, 3, for example. I integrated it was 3t. If I now have to divide it by inductance, if I divide it by a large value, that amount of ripple will be small, right? The amount of ripple will be very small. If I divide it by a small number, then the amount of ripple will be large, right? So inductance here will automatically change the value of the peak-to-peak ripple through an inductor. Yes? Because it affects the slope, right? It's the slope. The slope here is the integral of the voltage divided by the inductance. That's the slope of this line, the inductor current line. And same thing so how do you size the inductor then? So the sizing of the inductor will depend on, we said what? L is equal to delta lambda over delta I. Delta I is a spec. By the way, this is the way I size it, right? The book gives you just equations straight. I mean, you don't need to follow I'm trying to explain to you the physics behind coming from the waveforms. But in the book, you can use the equations that they have in the equation sheet, and they use that. But basically, this delta lambda is the integral of the inductor voltage. So if you go under this the voltage waveform here, this is the inductor voltage waveform. So this integral here is what we call delta lambda, the flux linkage, right? It's the amount of flux linkage that is surrounding the inductor when you've placed a positive voltage across this terminals. That's this area here, right? And this delta I is a spec. You spec that. So it's a specification from load. You want a load your load requires a nice smooth current with very low ripple, for some reason, right? Because it's a very precise sensor, because it's running image, whatever. And there are certain loads that require very very high precision voltage and current with very low ripple, and certain loads don't really care. So I have my delta I have my delta lambda, and I can calculate my inductance from there. So what happens if I increase switching frequency? What happens to my ripple when I increase switching frequency? For the same value of inductance. For the same value of inductance, what happens to my ripple current if I increase switching frequency? So this is fixed, right? Inductance is fixed. I'm asking what happens to my ripple, so this is my question, right? And then when I increase switching frequency, so what is the effect of switching frequency on my delta lambda, right? And I said delta lambda is this area under this curve. If I increase switching frequency, what happens? These waveforms will shrink. Like all these waveforms will shrink. Right? So the area here will become smaller. Right? So the duty ratio will remain the same. Because if you go back to the slides, if you go back here, for example, right? If I want a certain output voltage, my duty ratio will always have to be a fixed value. So if my input voltage is Vs is 10 volts, and I want an output voltage of 5 volts, so what's my duty ratio? Half, right? So I always will have to have a duty ratio of half. But is this equation talking about switching frequency at all? It doesn't, right? So I can get the same output voltage, but at a very different switching frequency, right? But I will still have to maintain the same duty ratio. Still have to maintain the same duty ratio, but I can change the switching frequency. If I change the switching frequency, what effect does that have on my ripple current? If I change the switching frequency, this red area becomes small. So delta lambda becomes small. Delta lambda becomes small. For the same value of inductance, my delta I will become small. Right? Right? This is the same value. Delta I is what I'm trying to figure out what's happening to it, right? So L is the same, and delta lambda becomes small. So delta I is proportional to delta lambda, right? Delta lambda is equal to delta I. So delta lambda over L is delta I, right? So this decreased, so delta I will decrease, right? Because of the switching frequency change, right? So increasing the switching frequency allows you to use smaller reactive elements to deliver the same amount of energy, maintaining the same ripple. If you're going to increase switching frequency, you can use smaller reactive elements. Or if you can maintain the reactive elements, then to decrease ripple, you can increase switching frequency, right? It's directly proportional. So is everybody okay now with the buck converter? This is a step down or buck converter, yeah. So if we look at what they're saying in the textbook, let's go through how they explain it in the textbook. So, and they talk about the output voltage waveform, so being equal, and again, nothing changes because the Vx waveform here looks like what? Looks like this pulsed waveform, correct? So if I want to calculate the average value of this pulsed waveform, it's the integration of voltage over the period. So the integral of voltage over the period will equal to the input voltage multiplied by the duty ratio. It's the same thing here. They're saying it's the same thing. They don't draw the waveform in this text in this slide, but the waveform is, again, we drew the waveform for Vx before, so we know that what this does is this is a low pass filter. Only allows the average value to pass through, right? So I have a waveform here with an AC plus DC. This has an average value of a certain value. This is what's going to go through my filtering element here. One thing I want to note here as well is if I look at my inductor current, this is my inductor current waveform. Does it ever touch zero? It never touches zero in this case, right? So since it never touches zero, we call this continuous current mode. Continuous current mode. So continuous current mode. Okay, so meaning that the inductor current never touches zero. What happens for the same value of inductor capacitor? What happens if I use a larger resistance? If I use a larger resistance, what's going to happen? Exactly. If I use a larger resistance, then I'm consuming less average current. Does the ripple change? No, because the ripple depends on the average voltage that you're putting out. I'm putting out the same voltage, right? I'm putting the same voltage at the output. That means that my duty ratio will not change, right? Because this, we said here, if my output voltage is the same, that means the duty ratio will never change, right? So, but my load now is consuming less current. So my load is consuming less current, but my duty ratio did not change. If my duty ratio did not change, and I did not change my circuit, meaning I did not change my L's or C's, right? So if I did not change my L, and I did not change my my duty ratio, meaning my delta lambda is also the same, my delta I will be the same, right? So these are all three the same. So my delta I, delta lambda, and L will be the same. Same thing with the capacitor. With the capacitor, my delta Q will be the same, and my delta V spec, my delta V will be the same, right? But what's going to happen? My average current will fall down, right? We said this average value of current is what's going to go straight to my load, right? If this average value falls down, while the ripple has not changed, we said ripple current did not change. Ripple current did not change, but I keep reducing my average value. What's going to happen at some point? These 2 points will become equal. And then beyond that, if I reduce my current, if I reduce my load current more, then I will end up with a current waveform that looks something like this. Is called discontinuous current mode. Actually, discontinuous current mode starts when you are in when the current waveform first hits 0. This is the initial point where you have discontinuous conduction mode. Beyond that, you're in discontinuous mode. But this is a critical point. This is a critical point. How can you okay, for the same, if you want to make sure that you don't fall into discontinuous mode, and you are given your load, you have a certain load here at the output of your converter, and this load is consuming a certain average value, right? So how would you make sure that your converter is not operating in discontinuous mode? Exactly, right? Because we said that this is my delta I, right? This delta I produces a certain value of average current, right? This delta I waveform 1 produces this waveform 1 average current. How about this waveform? How about this green waveform? What's the average value of current? Pretty much the same, right? Pretty much the same. So there's an infinite number of values of inductors that will change delta I, but will have the same average current flowing through the inductor, right? So part of the design procedure is to make sure if you want to operate in continuous conduction mode, then you have to make sure that your inductance is greater than a certain minimum value, right? So that's one of the equations that you will have in the textbook. That's something to consider. And you can do that without the equations. You can go through the waveforms that we went through, plugging in your average value, drawing everything to scale, all the waveform values to scale, draw your average value of current, and you will figure out how much ripple you need to basically make sure to design the proper size inductor in. And we will discuss discontinuous mode as well. There's nothing wrong with operating in discontinuous mode, right? So in discontinuous mode, what's the difference between continuous mode and discontinuous mode from an inductor size perspective? Exactly. Discontinuous mode has a smaller size inductor, so L is small. So if you, for some reason, from a design consideration, need to have a small inductance because of space, because of, I don't know, you cannot find the proper value of inductance, because of whatever reason it is, then that's a good way to go. You can operate in discontinuous mode. There's nothing wrong with that, right? If you have a power supply that will sometimes operate at no load for quite a bit of time, or a very light load. You have a power supply that operates at a very high load and then a low load. Very high load, then a very low load, right? If you design it to operate in continuous mode all the time, then you're going to do what? Then you're going to have to design it for the lower value of load. So you're going to have to try to size up the inductor to maintain continuous current, even though the average value of current is very low. That would be a huge size inductor. So in a case like this, maybe you will operate for light loads, you operate in discontinuous mode. In higher loads, you operate in continuous current mode. What is the difference between both cases from a control perspective? from a control perspective, in discontinuous mode, okay, if you took 420, have you taken 420? You are taking it now. So what kinds of systems does Dr. Nunu talk about? For you to be able to draw this G of S, you're deriving this for what type of system? Nonlinear systems? They're all linear time invariant, right? So time is not a factor in the system. The system has a frequency response irrespective of time. So we have somebody standing here. Anytime I will push him, he will fall up. He will fall over. It's not because it's morning or evening or afternoon, right? So it's a linear time invariant system. So if I push him hard, he will go further. If I push him soft, he will go slower. It's a linear system, right? But a non-linear system is something we don't cover in 420. In 420, we cover only linear systems. Non-linear system, you can push and the guy will push back, or you push and he will jump. You don't expect that, right? You expect if you have something that you linear, you expect you push, for example, it will move forward. So that's like a car accelerator, right? You're pushing the accelerator. You expect the car to move forward, and you expect it to move forward in a proportional fashion. You don't expect when you push your car on the accelerator to move very slow, and then you push a little bit further, it goes very fast. You expect that your increases in acceleration on your pushing your foot on the pedal is linear proportional to the output, right? But nonlinear systems don't behave that way. This continuous mode is like a nonlinear system. So there is a control theory to govern nonlinear systems, and there's ways to move nonlinear systems to maybe several linear systems. For example, you can operate it in that fashion, and the control theory is there, it exists, right? But in continuous conduction mode, our power supply looks like a linear system. And we will derive what that linear circuit looks like at the end of the chapter. And we will see that it's now very easy to control a power supply in continuous conduction mode. It's really simple to control. Also, what happens is the transfer function changes, meaning the gains, also the output changes. So maybe in a linear system, you press your foot on the pedal, push it 1 centimeter, you increase the acceleration by 20 kilometers per hour. Another 10 centimeters, another 20 kilometers per hour, so on and so forth. In a nonlinear system, maybe at the beginning it's every centimeter is 10 kilometers per hour, and then every 10 centimeter becomes 20 kilometers per hour, and then every 10 centimeters becomes 30 kilometers per hour, right? So it's you will have to control it differently. If you're in that high speed range, and you want to bring it down to a certain have a certain set speed, you are climbing a hill now, and you want to change and make sure you're maintaining your cruise control is working properly, right? So your cruise controller in this case has to respond to very sharp changes in speed with small variations in the accelerator. Versus your cruise control system will have to behave differently if you are in the initial range where your sort of the increases in the acceleration are proportional to sort of the increases in your foot on the pedal, right? So you can control both systems. There's nothing wrong with operating in continuous mode or discontinuous mode, right? So the design consideration. You may have to, a power supply, you may have to operate it in both modes, right? It just depends on how you size up your components, right? So here, that's why I went through this discussion, because here we assume continuous inductor current versus discontinuous inductor current, in which the inductor current returns to 0 each period, right? So I just wanted to make sure you're aware of that, and we will look at the equations for discontinuous mode later. So here they talk about the properties. The properties they talk about is, okay, what does this mean? This means that the inductor current is periodic. So I'm not concerned about the transient period. And initially, the inductor does not have flux linkage its coils. There's no energy stored initially. So, and capacitor is not charged. So the voltage will have to rise. So same thing with inductor current. The inductor current will have to rise. But we are here ignoring all of that, and we are assuming if this was inductor current, I drew inductor current as something that looks like this, right? Where this was my average value of inductor current, which in the buck converter case was also equal to the average value of load current. Only in the buck converter. In the boost converter will be different because the circuit topology is different. And this was my ripple current, my delta I ripple current. This was my average value, and this was what? I minimum. And this was an I max. This I minimum is equal to what? It's equal to my average value of output current minus delta I over 2. And I max is equal to, same thing, average value plus delta I over 2, right? And this is the average value. Okay, so if I know my average load current, I know my ripple spec, I know what my minimum value of current is, my maximum value of current is, right? So I'm not assuming that the inductor starts from 0. Okay, we're operating only in steady state in our analysis here. And then this is something we talked about before. Again, average inductor current is average inductor voltage is always 0, and then average capacitor current is always 0. This means that there is no DC voltage across the inductor. There's no average value of voltage across the inductor. It's only AC, right? It's the AC, only the AC component will be seen across the inductor. The DC component will not be seen across. It will look like a short circuit for the DC component, and the opposite for the capacitor. The average value of capacitor current is 0, so only the AC component of current will flow through the capacitor. DC component, capacitor will be an open circuit. And then, okay, for an ideal power supply, input power is equal to output power. For a power supply where we're gonna consider losses, the output power is equal to, input power is equal to output power plus losses, right? What else are we assuming? We are assuming that the circuit is operating in steady state, as I said, that inductor current is continuous for this analysis that we're gonna discuss now, and the capacitor is very large, and the output voltage is held constant at the voltage V output. This restriction will be relaxed later to show the value of finite capacitance, which we went through the waveforms, and hopefully we know how to do it graphically. The switching period is T. The switch is closed for a time dt, right? So D is the on-time duty ratio, for example. So the amount of time the switch will be closed for is duty ratio times the period, right? And open for 1 minus D times the period, right? So this is the off-time duty ratio is equal to 1 minus D in this case. And then the components are ideal. That's what the analysis in the following page assumes, right? We really don't have to go through the analysis if you understand the waveforms. So if you understand the waveforms, at the end of this analysis, what they're going to do is calculate the value of C and L. Can you calculate the value of C and L from the waveforms based on the discussion we had? You should be able to. But if you're not feeling comfortable with the physics, which I think you should try to make sure you feel comfortable with it, then they go through a standard set of equations and they calculate the value of L and C at the end of this anyway, right? So let's see what they do. So first they say the switch is closed. So you have the switch here for the step down converter. The switch is closed, meaning the diode is open, right? Both of them cannot be on at the same time, right? Because if they're both on at the same time, then I'm placing a short circuit across my source, right? So the switch is closed and the diode is open. If the switch is closed and the diode is open, they would like to calculate the voltage across the inductor. What does the voltage across the inductor equal? Supply voltage on one side and the output voltage on the other side, right? So the VL is equal to VS, which is the input voltage, minus VL, right? So VS is equal to VS, VL is equal to VS minus VL. And it also happens to equal LDI by dt, right? So the inductor voltage is equal to LDI by dt. And then what they did was they brought this L in the denominator here. So Vs minus V output over L, so Vs minus V output over L is equal to di by dt. Di by dt, they wrote it in a different fashion. How did they write? The di by dt is the change of current with respect to time for during this period, right? What is this period? This period is when the switch is closed. What happens when the switch is closed? When the switch is closed, we said that the voltage here is equal to input voltage, and then the inductor voltage is the AC component of that, right? So this is inductor voltage. right? So this is the inductor voltage. The inductor current is the integral of this flat value. The integral of flat value is this ramp, right? So what is di? What is the change in current during the period when the switch is closed? It's the movement of current, or the change of value from current from I minimum to I maximum, because this is when the switch is closed. The switch is closed for all this period, right? Until dt, the switch is closed, and then from here to here, the switch is open. But we're not concerned about that now. So from the beginning until dt, the switch is closed. So how far did the current rise? It rose a value equal to the ripple current, right? So they just said, okay, that is equal to delta I, which is the ripple, over delta t, which is the on time. On time is duty ratio times the full period. So it's percentage of the full period of where the switch is on. So they rewrite that as delta I through the inductor, so the inductor current ripple divided by the time where the switch is on, how long the switch is on. And that is equal to Vs minus V output over L, right? So, and then they write an equation for delta I, and they can rewrite that as delta I where the switch is closed is equal to Vs minus V output over L times dt, right? Okay, so are we okay with that? So this is delta I when the switch is closed. What happens to delta I when the switch is opened? So I started at I minimum, and I went all the way to I maximum. What happens when the switch opens up? Remember, we said that this is operating in steady state. In steady state, the current at every period, at the beginning of every period, is the same. So what do we expect to happen when at the end of the period when the switch is open? So now the switch is closed, the current started at I minimum, as now it's at I maximum. What will happen when the switch is open? What will happen at the end of the period? Current will be the same value. So what do we expect to see for delta I when the switch is open? It will be another equation, because the circuit will be different, right? I will open up this switch now, and this switch will be closed. And I will do the same thing, calculate the voltage across the inductor. One side now will be 0, and the other side will be V output, right? So I will still do the same process. I will follow the same process and calculate the voltage across the inductor and try to find an equation for delta I. And then delta I in the case where the switch is closed and delta I where the case where the switch is open, they're equal. It's the same current ripple. It's a spec actually given to you by the load, by your customer, right? So this is the logic, right? So, and then you're going to use this equality to find some relationships for, or the value of inductance, for example. Let's see what we can do with that. Yeah. So here, this is what I said we were going to go do, right? Find the value of inductor voltage when the switch is closed. The switch is open, sorry, now, and the diode is closed, right? So you find VL. VL is the voltage on this side minus the voltage on this side, so it's minus V output. And then we go through the same thing. I bring L on this side, so it's minus V output over L to one side, and then di by dt in this case is equal to the ripple current through the inductor divided by dt. Which dt? It's now the period when the switch is open, right? Switch was closed for capital D times capital T, and now it's open for 1 minus capital D, 1 minus the duty ratio times the period. So if it was closed for 0.4 times 1 second, now it's open for 0.6 times 1 second, right? So that's this, and then we do the same thing, solve for di. Solve for di when the switch is open now, right? But we know that di when the switch is open is equal to di when the switch is closed, so I can equate both equations. If I equate both equations, what do I see? I have this equation, it's a function of L. This equation is a function of L, which is nice. I have input voltage, I have input voltage in this equation. I don't have input voltage, but I have output voltage in this equation. So I have an equation now relating what? I have equations relating my input voltages. Oh, here, I skipped one. Here. I have equations relating my, fine, delta I when the switch is closed plus delta I when the switch is open. So your current rises and then falls down. So the sum is what? The change in delta I. we say there is no net change in current over one period, right? So there is no net change in delta I over one period. So delta I is positive and when the switch is rising, delta I is negative when the switch is open, right? So they're equal to each other or equal to the negative of each other, or the addition of them is equal to zero, whatever you want to call it, yeah. But we have two equations now that contain certain variables that are interesting to us. So this equation is Vs minus V output over L. This equation is V output minus L over 1 minus D times T. I end up with what? If I solve for V output, I end up with this simple equation. So you go ahead and solve it. Yeah. If you go ahead and solve it, you'll end up with this equation. This equation, where did we see it before? Right? V output is equal to Vs times D. Right? So it's the same. I mean, and it makes sense, right? And this was what was this? This was a simple step down converter, right? This was a simple step down converter. I was taking my input voltage, and I'm using my switch to extract a certain average value part of that to take to my output, right? So if my input was 9, I'm only taking 4.5 average value to the output. Yeah. So this is a step down converter. So you expect the output voltage equation to be the same, right? So that's where this derivation is very similar to what we've seen before. What else? What else can I do with the equation that I found? Okay, besides coming up with the output voltage equation, we said that I want to be able to calculate my inductance and capacitance values. So we have given our average value of load current. Again, load is defined. So given the fact that you have your average value of load current and you know your delta I, we know that the I max is equal to the average value of load current plus delta I over 2. And I minimum is equal to average value minus delta I over 2. I can use delta I when the switch is closed or delta I when the switch is open, whichever is convenient for me, whichever helps me to solve some problems, right? Because they're the same, they're equal in value. Delta I is exactly the same. Yeah. So, but what's interesting for me, I want to make sure that this point here, if I want to operate in continuous conduction mode, I want to know where is the critical value of inductance. So what would I do if after I find the equation for I minimum? Equate it to 0, exactly. So if I equate it to 0, meaning I'm bringing this point all the way down to 0. If I bring this point down to 0, I have an equation here that includes what? My resistive, my load, my output voltage, my inductance, my duty ratio, my frequency. So what does this tell me? It tells me that, okay, fine. First, I found my duty ratio from my input voltage. So I know what my output voltage is. I found my duty ratio because I have a certain input voltage, right? I mean, it's you have 10 volts, operate at duty ratio 0.5, your output voltage is 5, right? So I know the output and D now. So given the output, given D, given my load, which is known, I can now play with what? The switching frequency and the value of inductance to make sure that I don't ever go below a critical into this continuous conduction mode if I don't want to, right? Switching frequency, you will fix it. Typically you want to fix it. Typically you want to operate with as high a switching frequency as possible. As possible means as possible for your switch to operate and your environment to allow that to operate. Because again, if you remember very early on, we said that when you switch when we were talking about switches, we said that if you're trying to switch your switches, right? If this is the current flowing through the switch, I switch, this will be V switch, right? As soon as you turn the switch off, current will take time to fall down. There's a T rise and T fall. Remember that from the very early on? And voltage will rise as well. So there will be losses. Every time you switch, there will be switching losses. Okay, so there will be switching losses. These switching losses depend on the value of voltage and current. Right? So you want to be able to switch fast. How fast? How fast will be limited by your switching losses. It will also be limited by, okay, if you want to switch very fast and you still want a duty ratio of 0.5. Okay, so let's say I want a duty ratio of 0.5, and this is 1 per unit time, right? And my switch needs, I don't know, 0.1 per unit time to bring the current down. That means I cannot, this is the time needed for the current to fall down. There is finite time required for current to fall down. That means even if I try to increase my switching frequency, which means move this point to the left, if I want to maintain my 0.5 duty ratio, I won't be able to. Right? But at some point, I lose control of my duty ratio. Right? If I keep increasing switching frequency, my switch needs time to turn on and turn off. Right? I keep trying to do this faster and faster and faster, and still try to control duty ratio. You can't. You need 1 second to get out of this room. Right? It's finite. It's a finite amount of time. You cannot read a textbook. And I need a good example of that. But anyway, I think. So I hope you get the idea here, right? The switch needs time. The current in the switch needs time to go up and go down, and you need it to go up and stay up for a certain period of time, which is your duty ratio. If the period of time if how fast you want to do this keeps shrinking in time, you can no longer go up and go down and stay up for 50% of that period of time, right? So there's a limit on switching frequency dictated by your rise and fall times. Also, there's a limit on switching frequency related to your amount of power losses. Power losses you can sort of play with because, okay, I can put a cooling system, but then it means you're putting something big, right? So you can, even though you're allowed to, you can tolerate more power losses, but you have a big piece of equipment. So you're losing the benefit of increasing switching frequency to decrease the size of your LNC, right? So it's a big compromise. Okay, you want to create the smallest package possible versus you want to create the most efficient package possible. The most efficient package possible will be what? Will be something with a large inductor, large capacitor, and you can switch at a very low switching frequency, because then you don't have switching losses playing the effect, and you don't have large inductor resistances and capacitor ESR. So you're nice. You end up with something this big. But now you want to end up with something this small, doing the same function, converting 10 volts to 5 volts. How do you do that? It's an optimization algorithm. It's an optimization process here. Okay. So we'll stop here. Continue next time. I hope the physics of the interaction of all the elements and the circuits are